So today we're going to be looking at motion in one dimension, and in particular we're going to be looking at acceleration, and to keep things simple we're going to look at cases of constant acceleration. So you can see here, as in the lab it describes, if an object is falling under the action of gravity, the acceleration is going to be equal to g, which is 980 centimeters per second squared. That's vertical acceleration basically at the surface of the Earth. This value does vary a little bit depending on where you are, what your height above sea level is, how many big mountains are around you, how many iron deposits are below you. But in general, it's mostly pretty close to 980 centimeters per second for most places on the surface of the Earth. Another extreme case is if you have a body on a frictionless surface. It can have some velocity, but if nothing is pushing on it, then the acceleration will be zero. And so that's this horizontal motion equation here with a equals 0. But the case we're going to be looking at today is described by this geometry. There's a height and this hypotenuse that we have basically a cart moving on a frictionless track that's set at an angle relative to gravity. So gravity is going straight down in this picture. H is the height of a triangle that describes the track that the cart is on. So here's the geometry, and Galileo's hypothesis that we're going to be looking at today is that A, the acceleration of this thing, is going to be g, the acceleration due to gravity, that's the 980 centimeters per second squared, times h over d, where h and d are these sides of the triangle. So the bigger h is relative to d, the greater the acceleration. And this checks out with these two examples because, sorry about that, because if h is 0, then you have horizontal motion, and a is going to be g times 0 over d, which gives us an acceleration of 0. And if h is equal to d, because this is the right triangle, that means that basically it's going straight up and down, and so then you have a equals g times 1, so the acceleration would be equal to g if it was going straight down, which makes sense and checks out because that's what happens if you drop something. So this is the setup we're going to be using today. This is the cart. They'll be moving on the track. The track is 2 meters long, and it's got this blower hooked up to it. So if we turn on the blower, it's like a one-dimensional air hockey table. So there's a bunch of air coming out of these holes. It's really loud when it's on, but when it's turned on, the cart will slide freely back and forth along the track. So I'll just do that really quick so you can see. You can see it bounces off the end there, but in between, it's going at a pretty constant velocity. We'll actually do a measurement in a minute. We'll check and see how constant that velocity is. But you can see it moves pretty smoothly when the air is on. And the way we're going to measure these screws connected to the cart are in close proximity to this metal wire and this metal tape. And that wire and tape are connected to a high voltage supply here. And the way that this spark timer works is it generates a high voltage at regular intervals, and whenever there's a high voltage applied, it'll spark onto that yellow tape. So if I press the button to turn on the spark timer right here, you can see what happens. We get a little spark, and we can change the frequency of those sparks with this dial. Right now it's set to 60 hertz, which means that it makes 60 little sparks per second. So if the cart is moving along the track and making 60 sparks every second, that means on this paper tape, it's going to record 60 dots every second with the position that it's at. We'll do that all the way along the track. And then what we can do is measure the distance between those dots to figure out how far it traveled in a given time interval. So I'll set up and record an example and we can go through that measurement. So I've got the track set up. What I'll do is walk over, switch on the blower, give the cart a push, and hold down the button while it's moving across. We'll record a bunch of sparks on the tape and then take a look at the measurement. So I've taken the tape off of the track and they're pretty faint, but if you look, you can see little dots on the tape. Those are marks from the spark. And so those are position recordings that happened 60 times a second. So if we want to know the velocity of the cart when it was right here, we can take this position, see how far it went, and that delta x is the distance between these two dots, and the delta t is the 60th of a second, and we can make a ratio of those. The delta x over the delta t is the v, velocity of the cart. So what I'm going to do now is I just have an arrow on here. I haven't labeled anything else on the tape, but what I'm going to do is count out dots and circle every 6 so that our delta t is going to be not 1/60th but 1/10th of a second. That'll make some of the math easier, and we can figure out how fast the cart was going both when it was at the start of the tape over here and when it was at the end of the tape over there. So I'm going to go ahead and mark out the tape, and we'll take a look and see how that works out. So I haven't measured anything yet, but while the cart was moving across the track, I counted, and it took about 4 seconds to go the 2-meter length of the track. So I'm going to write down before we measure that my estimate for the velocity is going to be about delta x over delta t of 2 meters divided by 4 seconds. So that's equal to about 1/2 of a meter per second. So now what we can do is look in detail at the tape. I'm just going to move the camera around so we can look a little closer. And you can see where I have this marked. Right here where I decided to start measuring, there's a dot, and I'm going to line up the ruler. Let me zoom in a little more, move the camera a little closer so that's easier to see. So there's a dot right here, and I lined up the ruler so that it's at 10 centimeters. And then there's another one right here, and it looks to me like it's at about 14.9 centimeters. So then for this measurement, my position change is going to be 14.9 minus 10 centimeters. And what might be a little harder to see is I skipped over 6 spaces. So if I move the ruler back, here you can see there's a dot and then 1 step to the next dot, 2, 3, 4, 5, 6. So we moved over 6 spaces. And what that means is my delta t is going to be equal to 6 times 1/60th of a second. So we're down at the other end of the tape now, and I've got another pair of dots I'm going to look at. And one of them is at 110 centimeters, and the other one, it looks like, is at 114.8. So that delta x here is going to be 114.8 minus 110. 0.0 centimeters. And because it's 6 spaces again, my delta t is still going to be 0.1 seconds. So this one, it looks like, is going to work out to be, if you work out that math, 48 centimeters per second. So it's going pretty close to the same speed. We got one less in centimeters per second, but it's pretty close to the same velocity. It may have slowed down a little. It might just be that there's a little bit of noise in our measurement, so we can't really distinguish whether it was going slower or not. So comparing that to the 50 or 49 centimeters per second we got on the other measurement, this one's 48. We can calculate it out as a percent difference, but it's a difference of basically about 1 out of 50, a little bigger than that. So it's going to be about 2% or slightly over 2%. So that's pretty consistent with not too much acceleration for our level air track. So what we'll do next is set up a little bit of an angle on the air track, and we're going to do the velocity measurements at 1 second apart. Instead of just that end of the tape versus this end of the tape, we're going to set them up to do them exactly 1 second apart, but we're going to be doing the exact same type of velocity measurements that we just did. So to do our accelerated motion, we're going to put the track at an angle, and you'll notice it's got a foot here and the 2 feet over here. And what we're going to do is take one of these wooden blocks, we'll measure the thickness, and we're going to put it underneath this foot. And what that's going to do is raise that end up. So we're going to have a triangle where H is going to be the thickness of this block, because that's how high the foot is raised off the table. And then D is going to be the length between this foot and that foot. So H, I'm going to measure with the calipers, that's the thickness of the block. And then D is going to be 100 centimeters, because that's the distance between these feet. This one's at the 50 on the tape, and the one over here is at the 150. So for all of the measurements coming up, D is going to be equal to 100 centimeters. And H is going to depend on the thickness of this block and how many blocks I have underneath the foot. So it looks like for one block, we've got a thickness of 18.66 millimeters. So if we want to record that in centimeters, it would be 1.866. So there's the track set up on the block. I'll go ahead and set up the tape, and we'll record with the spark tape again. So here's our tape from that run, and you can see I've labeled it with the height that we used, an arrow indicating the direction, and just take a look at the dot spacing here. We'll get a ruler lined up so you can actually tell what's going on. Okay, so there, I would say those dots look like they're about 0.5 centimeter apart, roughly. And if we move down way to the other end of the tape, you can see now the dots are much more like 1 centimeter apart. So the cart definitely sped up, as you saw in the video, and so that means the dots were recorded further apart. And now what we're going to do is count out the dots all along the tape so we know how long it's been recording, and we'll measure the velocity at the beginning and then later on, and using the time difference between those two velocity measurements, we'll be able to calculate an acceleration. So I'm just going to mark out groups of 6 all the way down, so we'll be stepping by 1/10 of a second, and I'll get the tape labeled, and then we'll take another look. So now you can see I've labeled the times on the tape, so I went ahead and circled this dot and decided to start here. So I labeled this t equals 0, and it skipped over 1, 2, 3, 4, 5, 6 steps. 6 steps in dots is 1/10 of a second, so I label this 0.1, similarly to 0.2, and all the way down the tape. Well, not that far, but I got here to 1 second and 1.1. So What this allows us to do is do a velocity measurement back at the start of the tape and see how fast it was going between t equals 0 and t equals 0.1. And then we'll do another measurement over here and see how fast it was doing between t equals 1.0 and 1.1. So we'll have two velocities, and the two velocity measurements are 1 second apart. So we can look at how much the velocity changed, and we know how long it took to change because this measurement is 1 second after the first one. And so then our acceleration is going to be delta v, the change in velocity, divided by 1 second, because that was the time between the two velocity measurements. So this is at the start of the tape. You can see I have t equals 0 and 0.1. I'm just going to line up and hold the ruler here carefully. So I've got t equals 0 at 10 centimeters, and then t equals 0.1, looks like it's at 13 point, it's right between the 13.1 and the 13.2, so we'll call that 13.15. So then our delta x1 is going to be equal to 13.15 minus 10 centimeters. Now over here at the other end of the tape, you can see I've got 1.0 seconds and 1.1 seconds. Just going to set up, line up our tape for a measurement here. I'll put the 1.0 at 50 centimeters. And here now it looks like our delta x2 is going to be 54.95. Because again, it's right in the middle of the 54.9 and 55.0, so we'll call it that in the middle. 54.95 minus 50 centimeters. So now we have these two delta x's. This is how much the cart moved in the first tenth of a second, and this is how much it moved in a tenth of a second that was 1 second later. So we can calculate the velocity by dividing by the delta t here, and we can take this divided by the delta t of a tenth of a second and get the velocity here. And then since these two measurements were 1 second apart, we can look at the change in velocity and calculate the acceleration. Okay, so I'm getting ready to do our 2-block measurement. So we'll have the track at a steeper angle with 2 blocks under that foot, and it looks like our thickness, our h, is going to be 3.769 centimeters. 3.769. Alright, so I've marked out the tape and it looks like we got enough points. So for run 2 with h of 3.769, let's see, get this lined up. And I think our delta x1 looks like 16.2 minus 10.0 centimeters. So that's just going to be 6.20 centimeters. And move this down here. See if we can find our later measurements. And you can see there we've got 1 and 1.1 seconds. And this looks like delta x2 of 109.8 minus 100.0. So that's going to be 9.8 centimeters. And with that, you can calculate the V1 and V2 from those x's, and then you can calculate the A from the V1 and the V2. Okay, so for our third and final run, we're just going to go ahead and stack all three of these blocks underneath the foot. So, getting that measurement set up, it looks like we're at 56.65 millimeters. So that'll be 5.665 centimeters. Okay, so same setup as before. Here's our t equals 0, t equals 0.1. And lining up the ruler here, it looks like our delta x1 is going to be 16.1 minus 10.0 centimeters. So 6.1 centimeters. And moving down to this end, there you can see our t equals 1 and 1.1 measurements. And setting up the ruler there, it looks like our delta x2 is going to be 111.6 minus 100.0 centimeters, which will give us just 11.6 centimeters. So there's our delta x1 and delta x2. Okay, so that should be everything we need to fill out this table on page 4. I'm realizing right now I just made one mix-up in the notation, and what I was calling delta x1 is referred to as delta xi in the lab, and what I call delta x2 is referred to as delta xf. Hopefully that's not too tricky of a substitution to make. But the H, the first column in the table after the run number we measured with the calipers, D is going to be 100 centimeters for each of the runs. A theory you can calculate as G times H over D, so that's 980 centimeters, times whatever the H is for that run divided by 100 centimeters. The delta XI is what I call delta X1. The VI you calculate by taking the delta XI and dividing by 0.1 seconds. Delta XF is the delta X2, and again VF, you just divide the delta XF by 0.1 seconds. And then the A experimental you'll get by taking the difference of those velocities, the VF minus the VI, and then dividing by delta T, which is just 1 second because of how we arranged it. So hopefully that's enough data to work with, and you can get some results, compare them to the theory, and we can talk about the rest of the questions.